Okay, maybe we should get started. Hello, everyone. I am Baden. Sorry, I'm a postdoc at Stanford at Applied Physics, and I'm moderating this session. Today, we're happy to have Rafał Demkowicz-Dobrzański from University of Warsaw, from Poland. Rafał is an expert on quantum estimation and quantum metrology. He's an associate professor at the University of Warsaw, and today he's gonna talk about quantum metrology in the era of quantum information. Before we get started, I just want to remind everyone that post your questions in the chat box. We'll be taking the questions. I'm gonna help to basically take your questions during the talk or at the end, depending how the talk goes. Please.
Okay, so welcome everybody. I'm really happy to be with you. I see some familiar names on the list. So I want to tell you something that is at the border between quantum metrology and quantum information. I work in both fields, but mainly in quantum metrology. And at the first sight, it might not be obvious what this left-hand side of this picture can have to do with the right-hand side. So, for example, magnetometers or interferometers, what can it have to do with quantum error correction or tensor networks? Okay, so my idea is to show you some recent advances in these fields and something that may inspire you. If you are coming from quantum computing field, that there is something in quantum metrology that's interesting, and vice versa. Okay, I'm a theorist, so sorry for this slide. So this is what quantum metrology is for me, mainly. So we have some quantum channel, like here, this unitary channel, depending on some unknown parameter. And we can send some input state into it. Then we get an output state that depends on this phi. Then we want to measure it and estimate. So depending on the measurement result, we give some estimated value phi tilde. And our goal is to estimate this true value of phi as well as we can. And we are allowed to minimize over multiple of things. So here in this setup, we will be able to minimize over measurements, estimators, and the input states, while the channel itself is given. Okay, and we want to estimate this parameter. So this is basically, you can call it quantum estimation of a quantum channel. Okay, and one of the basic tools that we employ when analyzing such problems that help us to solve this problem, because as you can imagine, minimization over all these things by brute force is not something that can be done in general. So we use the concept of Fisher information a lot. And first, in its classical version, it's the quantity that appears whenever you have some probabilistic model. So you have some observations I, where the probabilities that you get result I depends on the parameter you want to estimate, phi. And then if you ask, what is the optimal way I can estimate phi from this measurement results I, then we have the so-called Cramer Rao inequality, this inequality here, that tells us that whatever estimator we choose, provided it is unbiased, or strictly speaking locally unbiased, which means basically that it tracks the true value of parameter. Okay, then the variance of this estimator can never be lower than 1 over Fisher information, and Fisher information is given here. It's not very important what is the actual form. It's important that it is higher the faster the probabilities change when you change the parameter. Okay, so that's why you have these derivatives of probability distribution over parameter phi. Okay, and then you have a quantum version where you are not given this probabilistic model where you have these probabilities, but you are given quantum states, this psi-phi here. And now, in principle, you can choose different measurements, this pi-I, that will only then give you this probability distribution. Okay? And then you can ask, okay, if I'm allowed to choose arbitrary measurement and estimator, what is my bound on precision of estimating phi? And this comes with the so-called quantum Cramer Rao inequality, which tells us that whatever estimator, unbiased estimator, and measurement we choose, we cannot beat 1 over quantum Fisher information, where quantum Fisher information is now only a function of the state we measure and its derivative. Okay, so how fast this state changes, and if this is new to some of you, then you should keep in your mind that basically what I'm telling you here, when you restrict yourself to pure states and to channels which are unitary channels generated by some Hermitian generator, so that this u phi is e to I some operator phi or t as written here, then you can easily recover here a variant of formulation of a time energy uncertainty relation. So if you want to estimate time based on how your state changes when you evolve it for a certain time t, and you want to estimate this t, then from quantum Cramer Rao inequality we get that variance of estimator of t is lower bounded by 1 over 4 variance of Hamiltonian on your state. Okay. By the way, I will be happy if you interrupt me, because otherwise I may get depressed. That nobody is listening, or that's okay. So any questions at this point? No.
I don't see any questions though.
Okay. Okay. So now, when we have these tools, we can ask some more specific questions. So imagine the simplest scenario where we have a single qubit and we want to estimate the angle of rotation. So we have this unitary. And then we ask, okay, if we are allowed to use this quantum channel n times, how well we can do with estimating phi. So the basic scheme would be to use n channels independently, so use n qubits and evolve each separately and measure each of them separately and then estimate. And this we will call uncorrelated scheme. Or we can be a bit more general, more clever, and ask what can we do if we use entangled states and measure them collectively. This we will refer to as entanglement enhanced scheme. And if we have quantum Fisher information as a figure of merit, we can simply ask the question, what is the maximal quantum Fisher information we can obtain in these schemes? And it's very easy to show that in this uncorrelated scheme, the optimal single qubit state is just a state on the equator, and the quantum Fisher information for it is 1. Whereas if you have a product state, quantum Fisher information is additive, and that's why for this n qubits it's n. While if you have this entangled states, you can find this G8Z state or Nun state if it was written in different notation. And it gives us n squared, and this we call that we have a quadratic gain in estimating parameter thanks to use of entanglement. Okay. This would be a simple message. Still, this parallel scheme as depicted here is not the most general you can imagine. Actually, if you formulate the problem in a way that you are allowed to use your unitary n times, but apart from that, you are free to do anything that quantum mechanics allow you to do, then the most general scheme actually is this one, where you send a single qubit through this channel, while additionally you have arbitrary number of ancillary systems, and then you perform some collective operation on all of them, and then again this unitary acts on one qubit, and so on and so on, and then in the end you perform collective measurements. This scheme is more general than this parallel scheme because in principle it allows us to use adaptive strategies. So you can imagine some of these lines go to the end, the measurement, and depending on the measurement result, you have some construction where you have like conditional unitaries that depending on measurement result, different unitary acts at some point, and so on and so on. And this is the most general scheme for this. But interestingly, if you have unitary parameter estimation, like noiseless parameter estimation, as we discussed now, it appears that you have no advantage here compared to this parallel scheme depicted before. And still the maximum Fisher information, if you optimize over all input states and over all these control operations here, is n squared. Okay, this side. Okay, so this is very simple, but interesting things start to happen when we move from ideal noiseless scenarios to real life scenarios where we have decoherence. Okay, so we formally replace our unitary channel with some completely positive map quantum channel, that quantum noisy channel. Okay, so we can always write it using Kraus decomposition, and then dependence on the parameter we will have in this Kraus operator. Okay, so for example, to make it more physical, this is like transition from ideal interferometer to interferometer that takes into account losses, or from ideal, I don't know, magnetometry or frequency estimation in two-level atoms to the same task but taking into account dephasing of atoms. Okay, and in particular, it often happens that the models we are interested in have this kind of decomposition where this noisy Kraus contain this unitary channel multiplied by noisy Kraus, which does not depend on the parameter we are interested in. In these schemes, it would be so. Of course, it's not always like this. Sometimes we are interested also in parameters that are in the noisy part, but I will mostly focus on these problems where we are interested in the unitary parameter, while the noise is something that causes trouble for us. Okay. So now, when we have noise,
Rafał, I'm gonna may I interrupt you. There are two questions.
Sure.
Sharon is asking actually what K is standing for here.
What? Once again, please.
The K operators. What are they? Sharon is asking.
What are they? They are Kraus operators. So formally, any quantum channel can. In general, when you take into account decoherence, you replace unitary operations with completely positive maps. And the general form of completely positive map is as written here. So it's like a generalization of unitary evolution to take into account noisy evolutions. And then these K operators, they are called Kraus operators. And they can formally, they can be any operators, like they are neither, they don't have to be neither unitary nor Hermitian nor anything. They can be some complex matrices. And they
Thank you so much.
Okay, that's good. So any other questions? Yes.
Yeah, Julian Martinez asks, how do you find optimal estimator to saturate the quantum Fisher information?
Okay, so for a moment I don't care, okay, because I will just focus on deriving bounds. Okay, so this Cramer Rao bounds tells us that we cannot do better than something, okay, and then it's fine, provided that these bounds are tight enough. And for example, we have some strategies with which we can achieve these bounds. But you're right, formally, just from what I'm saying, it's not clear how to saturate this bound. And this is a bit subtle subtle story, because the general construction tells us that we can always find locally unbiased estimator that is optimal at a single value of parameter phi. So, so provided I know what is phi, I can construct a locally unbiased estimator that with up to the first order in changes of phi, it will properly track the changes of phi, and it will saturate the quantum Fisher information bound, okay, always. But it's not very practical because first, you usually a priori, you do not know how close to the true value you are, okay, and whether you can really use this estimator. So there are like, so this is the first statement. The second statement is that provided we can repeat experiment many times, then asymptotically, for many, many repetitions of the experiment, we can prove that the so-called maximum likelihood estimator will always be optimal, and it will be optimal uniformly. So it will be optimal in a big range of parameters, not just locally. And this is much more practical, but it requires you to work in multiple repetition scenario, which is not always what you want. Sometimes you want to know what I can learn from like a single shot experiment. Okay? Yeah, so I'm not sure if it answers.
Yeah, thank you.
Okay. Good. So let's go on. So now we have these noisy channels, like we discussed on the previous slide, and now we can ask the same question: can we have a strategy that gives us n² scaling of Fisher information? So we will refer to this as a Heisenberg limit. So, or Heisenberg scaling, maybe I should be more precise. Or the noise makes such a mess that we can only expect scaling which will be linear with n. Okay? So this is a big question. For a given noise, can you somehow protect your quantum evolution in a way to have a scaling which is characteristic for noiseless unitary parameter estimation, or you are forced to accept the fact that the scaling will be linear? Okay? So this is a non-trivial question. And if you use quantum Fisher information, you realize that it's very difficult now to answer this question by brute force, because if we have noise, we deal with mixed states and not pure states. And for mixed states, the Fisher information, formula for Fisher information is not so straightforward, and it requires, in general, finding the eigenvalues of the density matrix rho phi, which can be done numerically, but it's difficult then to conclude some general, general statements that would be valid in asymptotic limit of many particles and many use of the gates, and also to say something what can this adaptiveness do, and so on and so on. So it's very challenging. But there is some beautiful property of quantum Fisher information, which is the following: if you have a quantum Fisher information for a mixed state, you can consider purifications of this mixed state. Yes, so extend your space with some environment space and consider some pure state for which your density matrix is the reduced density matrix. And then, of course, if you consider such a purification, then you are not surprised that the Fisher information will be larger for this purification, because in principle it contains more information. But you can prove that there is some purification that is like bad enough that it contains no more information than this mixed state. Okay, so if you minimize over all purifications of your mixed states, you can find at least one for which Fisher information is equal to this Fisher information of the mixed states. And this observation may be helpful in deriving the bounds, because if you are clever enough and you find a good purification, you may be able to calculate quantum Fisher for it analytically or in a simple way. And if it's clever purification, it will give you a good bound, a tight bound maybe. Because, okay, in fact, you don't need really to minimize over these purifications. It's good enough to find a good, a good one that will be close enough to the true value that it will provide you some meaningful information, okay? So this is the idea. I will not go into details of this because it was a long story how to make something useful out of this observation. And I will just show you the results that some groups and us as well obtained a couple of years ago, and which are based on this observation. So the observation can be also rephrased in a way that different purifications of a state, if you think now on the level of quantum channels, if you are familiar with the fact that a quantum noisy channel can also be distilled to a unitary on a bigger space, right? Then you realize that different purifications or distillations of your noisy channel, that you can associate with each such purification a different set of Kraus operators on the level of this physical space you started from. So in other words, if you are given a CP map, you have a Kraus representation, but these Kraus representations are not unique. You can find different Kraus representation, so different set of Kraus operators that give you the same quantum channel. And they, in fact, correspond to different ways of purifying your noisy evolution. Okay, and we use here this idea in this way that we consider some Kraus representation, but then we consider some equivalent Kraus representation, and equivalent Kraus representations are obtained from a given Kraus representations by some unitary by such a formula where V, Ij are entries of a unitary matrix. So you are mixing your Kraus operators with a unitary with an entries from a unitary matrix. And here the non-trivial thing that we do is that we allow these entries of this unitary matrix to depend on the parameter we want to estimate. And that's why this Kraus representation, this K tilde, will change in a non-trivial way. It will be still the same channel, but from the point of view of the bounds we derive, it will give us some non-trivial change. And now I just quote the result, which was obtained as like in these papers, starting with Fujiwara in 2008, and then in 2014 we derived this bound in this most general adaptive scheme. So this bound may look a bit scary at the first sight, but it is not at all, because it answers very difficult questions. So it answers the question, what can be maximal quantum Fisher information in such adaptive schemes if you allow any uses of your channel and arbitrary adaptive strategies, and it is expressed in terms of objects. So this alpha and beta are operators which are just single channel operators. So they are constructed from Kraus operators of a single channel. So of a channel that acts on a single probe. These dots are just derivatives of these Kraus operators. And I use here this vector notation. So this bold K is a vector of Kraus operators. Okay, so actually this alpha is a sum of K dot dagger I, K dot I. Okay, so sum over indices over all Kraus operators. And this beta thus differs that the dot is over one term here. And these norms are just operator norms. So maybe I will pause for 10 seconds so you can digest this formula, but it looks maybe a bit nasty, but on the other hand, it's very easy to use because it just requires you to minimize over, okay, now there is this minimization over different Kraus representations, but of a single channel, okay, which is doable. Okay, because usually you think, I don't know, you have qubits, you have many qubits, so this will be just a single qubit channel. Okay, or you have maybe some bigger systems, but usually they will not be very big. You consider many of them, but elementary system will be very small. Okay, so I'm not sure if there are some questions at this point.
Yeah, Mark Wille has a question. Maybe I unmute Mark and he can ask his question.
Sure. Hi, Mark.
Oh, so yeah, this is an interesting bound. My question is if there's a link between it and the SLD or RLD Fisher informations of channels.
Okay, so okay, I would so by Fisher information of channels, you mean if I take, I don't know, Choya-Miałkowski isomorphism for a channel and treat it as a state and calculate quantum Fisher information for it, yes?
You could allow for an optimization over inputs to the channels also, not just the maximum entangled state.
Okay, so I presume, okay, yes, sure, but in this case, as you say, I imagine that you will always have a bound that will scale linearly with n.
Mm-hmm.
Okay, because as you say, in this case, channels, you have like independent channels, and you have some quantity for each of this channel, and then you have like additive, you add it if you have n channels. So you will have a bound which either is infinite or it scales linearly with n.
I see.
So I would say that this bound is a bit more powerful because it contains two terms, linear and quadratic term in n, and sometimes they will coincide with the one you refer to. But in general, this bound, as far as I experience it, is always at least as good, and usually it's more powerful.
Okay, thanks.
Okay.
I have another question, and maybe you'll say this on the next slide, but this is efficiently computable by SDP, is that right?
Yes, yes,
okay.
Yes. Okay, I'm not maybe telling, yeah, I'm okay, I will tell it.
Thanks, sorry.
So, okay, so any other questions? Or no?
I don't
okay,
think so.
So, yes?
No, please go ahead.
Okay, so now, if you have this bound, it's very easy now to answer this question whether we can have Heisenberg or no Heisenberg scaling. Because as you see, we have this linear term and the quadratic term. So now, if you can find Kraus representation of a channel for which beta is 0, for which this operator beta is 0, then immediately this quadratic term vanishes, and you prove that quantum Fisher information can scale no better than linearly, which means Heisenberg scaling is impossible, and you can get some quantum enhancement, but it will be only constant factor enhancement. Okay, so to give you more intuition, what this condition beta equals 0 means. So recall that this k tilde is this unitary change of Kraus operators. In fact, because we consider quantum Fisher information, we only operate locally, we can restrict ourselves to this kind of transformations. Okay, I'm a bit late with time, so I would like to spend more on this, but I will go a bit quicker. So, okay, if you don't follow this considerations, I'm sorry. But okay, you can write this beta effectively that it changes your Kraus operators in this way, where effectively what is important is this generator of this transformation of this V matrix. And now if you ask, what does it mean beta equals 0? It means that I k dot dagger k is equal k dagger h k, where h is some Hermitian matrix. In other words, the question is, can you find this h matrix such that I k dot dagger k is within the span of products of Kraus operators? Okay? Hermitian span. Okay, so you use Hermitian coefficients for this Ki, Aj. To make it more intuitive, consider this subclass of problems that I referred to earlier, where we have this unitary encoding and noise. In this case, K dot dagger K will just be this Hamiltonian, so this generating operator of this unitary transformation. So condition for beta 0 means that beta is equal 0, or other words, Heisenberg scaling is impossible if Hamiltonian that generates your rotation, you want to estimate this angle of this rotation, is within space spanned by products of Kraus operators, okay, which describe your noise. So this is kind of intuitive that if noise is rich enough to somehow encompass your Hamiltonian within such a space, you cannot protect from it. Okay, and you are, okay, at least you cannot protect in a way that you have Heisenberg scale. Okay. Good. And so now you can ask the question, is it typical or not typical situation? So if you can find beta 0, this bound changes to this form, where we have minimization over Kraus operators with condition beta 0. And actually, it appears that it's kind of generic situation. So if you take a random channel, so like a full rank channel means it's a generic channel. So it's not a channel on the boundary of a set of quantum channels. Then you can show that you can always find beta 0. And then you can only say, okay, that's too bad. It's only Heisenberg scaling is lost. Okay, but then you can say, oh, at least I can find some coefficient that tells me how well I can improve over uncorrelated schemes using entanglement. And indeed, you can a bit. And this you can find out by semi-definite programming program, which is very simple to run. And this is as Mark referred to. And these are some exemplary models for which Heisenberg scaling is impossible. Okay, and you have also these coefficients that appear here, and you see that estimation of phi is case like 1 over square root of n, but here you have some coefficients which are better than if you just use independent qubits or photons or something. So that there is bad and good news. So bad news is that Heisenberg scaling is lost. Good news is that you have still some advantage. So maybe to make it more physical, now you all probably of you have heard about gravitational wave detectors, and in particular the fact that they are already using squeezed light in them. So last year they were reported detection events in LIGO and Virgo detectors where they demonstrated improvements thanks to use of squeezed light, and this was not a proof of principle improvements, but improvements in real operating mode of these detectors. So you can see this noise curves, and this green is with squeezed light. Okay, so there is some like 30% reduction of noise thanks to use of squeezing, which may not sound spectacular, but if you take into account that to obtain the same reduction, you would need to increase the power of the main laser by 85%, you realize that here something amazing happens, because you use very few photons in your squeezed vacuum state that you send to the usually unused port of a Michelson interferometer. You can say that you basically use 100 quantum photons to do the work that could be done by 10 to 20 added photons in the main laser. Okay, so this is shocking. I mean, how much you gain by using your 100 photons in a clever way. And from our point of view, one of the most also exciting things about these results is the fact that this improvement with squeezed light is actually reaching these fundamental bounds very closely if you take into account the level of loss in these devices. So basically, what we can say from our bounds is that given the level of loss in their interferometers, which is about 70% overall, there is no point of using more sophisticated quantum strategies because this one saturates the bound. So even if you could produce null states with 1,000 photons or squeeze your light 100 times stronger, it will not give you any noticeable advantage because of the level of loss you have in your system. Okay, so this is end of this first part, and I see I'm getting closer to the end of my talk, but maybe there are some questions at this point. No questions. Rahid?
I don't see any questions.
Okay, good,
maybe
good.
we can just
maybe I should
yeah.
go on because there is not much time. Okay, so now I want to give you some short message about our very recent results, which are related with what I just said. So the use of tensor networks in quantum metrology, if you are familiar with tensor networks, maybe it will be interesting for you. So from what I said, you should now realize that for generic noise processes, the typical behavior of precision you can achieve is as follows. So for small photon numbers or qubit numbers, you will see that your precision goes down at a Heisenberg scaling rate. This is log plot, okay? At a Heisenberg rate. But because of noise, for larger number of probes, this curve will flatten and will approach 1 over square root of n scaling with some coefficient that is quantum enhanced. Okay? So this is what we observe. So in reality, you should observe things like this. What does it mean? This means that you can obtain almost optimal precision if you have very many particles, like I know, million. Then there is really no point if entangling million particles. Probably it is enough to entangle, I don't know, 20 or 30 and then repeat this experiment. Okay? And it will already give you this quantum enhancement very close to this fundamental bound. So this is one message from this. So, okay, you can use weakly squeezed states, for example, as in this gravitational wave detection, or you can use this product of states with few entangled particles. And what does it mean? It means that it may be very useful to employ methods of many-body physics, in particular matrix product states. Because if we know that only weakly entangled states are sufficient, then it means that if we consider matrix product states, which, okay, I'll just briefly write it in this form. So matrix product states, for people who don't know them, are states that allow us to efficiently describe quantum systems in a big Hilbert space, provided they have some simple correlation structure, okay, that in some sense entanglement is not too complicated, okay, between them. And in this case, we have the so-called bond dimension D, which describes how sophisticated is the entanglement at a given partition between part of our system. And this results in quantum metrology imply that in principle you can find almost optimal quantum states within a class of matrix product states with low bond dimension. Okay, and this is an exemplary plot where we plot fundamental bound, and green curve is for product state, purple for matrix product states with bond dimension 2, and red for 3. And you see that we are approaching very close to this optimal performance. And very recently, we were able to formulate like a full computational procedure that operates on the level of matrix product states and in more general tensor networks for the purpose of finding the optimal metrological protocols. So in short, we are able to calculate quantum Fisher information for mixed states represented as matrix product operators, which in itself was not at all a trivial task. We are able then to perform iterative optimization procedure to find the optimal states. We are able to model not only problems where noise is uncorrelated, as I discussed before, but also models where noise is locally correlated, so still within this framework of local correlations, which fits well into this tensor network paradigm. And also it nicely allows us to numerically go formally to the infinity limit using the so-called infinite matrix product operator formalism, and obtain numerically these asymptotic coefficients if we cannot derive them analytically. Okay, I'm just telling this to people who are somehow familiar with tensor networks, because it's too fast to follow it if you are not familiar with this. But I want to mention that this is one of our very recent results, which I want to advertise to you. And for example, we could deal with estimating of magnetic field taking into account field fluctuations, which also can involve correlated field fluctuations. So that we have local correlations between fluctuations at different sides of our space. Okay, and we have results that really are very convincing, and they are very interesting, because we were not able to obtain them using the state-of-the-art methods that are, for example, the bounds I described to you are very difficult to apply to correlated noise models. Okay? They are good to apply to uncorrelated noise models, but not so much to correlate. Okay, so I told you about the tensor network stuff. Okay, maybe there are some questions. I hope that you add me this 15 minutes because the questions are on the way. So
yeah,
hope 15 minutes.
Maybe we can continue and we can take questions at the end.
Okay, so now I come to this quantum error correction thing, how it merges with metrology. So you remember that I mentioned to you that if Hamiltonian is within this space spanned by this product of Kraus operators, Heisenberg scaling is lost. But now you can ask the opposite question. If it's not in this span, can Heisenberg scaling be preserved? Okay, and interestingly, that's so. And this was proven in general in this paper by Liang Jiang group in 2018. It was only conjectured by us in 2017. And the idea is that basically, if this Hamiltonian is not in this space, we can correct all the noise. So all Kraus operators will be corrected, but because this Hamiltonian is not within this span, there will be some part of Hamiltonian like perpendicular to this space that will remain intact, and it will provide rotation in some effectively noiseless space. Okay, and this will give us Heisenberg scaling. So the idea is very simple. So now to make it more concrete, if you consider dephasing model, so rotation around z-axis and dephasing, so our Bloch ball shrinks like this, then you can quickly see that Hamiltonian is just sigma z, while Kraus operators corresponding to the standard dephasing, they are identity and sigma z. And now you can ask the question, is Hamiltonian in this space or not? Of course it is in this space, because one Kraus operator is sigma z and the other is identity, so identity times sigma z, and Hamiltonian is sigma z. So what does it mean? Heisenberg scaling is impossible, okay? And we can only get this c over square root of n, which I already mentioned before. But if in your quantum system somehow you are dealing with this kind of noise, so the dephasing is along a perpendicular axis, or actually it could be along any other axis apart from sigma z, then your Kraus operators are identity and sigma x, and now there is no way to produce something that you can write sigma z as. Okay, you have identity and sigma x, and sigma z cannot be written as a linear combination of identities and sigma x. This means that Hamiltonian is not in this space, and now you can expect Heisenberg scaling to be possible to achieve. And actually in this example, the error correction scheme that you can employ is very simple. So it involves just one ancillary qubit, and you just prepare an entangled state 0, 0 plus 1, 1, and you evolve it, and then you see that because noise is sigma x, if a noise happens, it will move your states to a space which spanned by 0, 1 plus minus 1, 0, which is orthogonal space to the space where you remain if you have just noiseless evolution. If you have noiseless evolution, you remain in this space 0, 0 plus minus 1, 1. And if the error happens, you move to an orthogonal space. And you can, of course, detect it and correct it. Okay? So there's standard error correction operation. And if you apply it fast enough, you can correct these errors and have unitary evolution and have Heisenberg scale. So it's very simple. But the construction given in this paper from 2018 gives you a general construction, how to do it for arbitrary models, where Hamiltonian is not in this span. Okay, so this is one side of the story. So quantum error correction can help you to achieve Heisenberg scaling for models that you can do it. Okay, so for models for which it is not forbidden. So last point, can quantum error correction field benefit from quantum metrology? Okay, so before we show that quantum metrology benefit from quantum error correction in some sense, and now we ask the opposite question. And the intuition is such, because we have such a powerful metrological bounds that tells us that generically Heisenberg scaling is impossible, maybe these strong bounds can tell us that some forms of error correction are also inefficient or impossible. Okay? Because if they were possible, they would violate metrological bounds. Okay, this is the logic. And it revolves around the concept of fault tolerance and transversality. So if you are in error correction field, you know that it is desirable to have encoding schemes where logical operation is represented as a product of physical operations, because this will allow us to control better propagation of errors in our algorithm. Okay, so basically, if you have some unitary, it will be ideal to be able to implement it, some logical unitary, it will be ideal to implement it as a product of physical unitaries. Okay, because then if an error happens at a given site, it will only stay on this site, while if unitary affects more qubits, a single error can propagate, can spread, and it's more difficult to control. I mean, to analyze such schemes. And there is some bad news in the field of quantum error correction, the so-called Eastin-Knill theorem, which says that if you want some non-trivial local error detecting quantum code, and you want to have universal set of gates, so not only, I don't know, rotations around z-axis, but the gates that can allow you to realize arbitrary logical unitary operations, then you cannot have at the same time universality and transversality. So this local property, yes, that you encode in products of physical gates. Okay, and now there is this theorem, and there is recently some interest in the approximate version of this theorem. Okay, so we agree that it's impossible, but now we ask, okay, it's impossible to have perfect error correction, but maybe if we allow some imperfection in this error correction, it's possible. And it will be interesting to study how this imperfection scales with the resources we use. So for example, with number of physical systems we use in our error correcting codes. And these are these two papers that study these problems, and they are very complicated and challenging to read. And we realized that we can answer this question using metrological bounds in a much simpler way. And we focused on this class of codes which are called covariant error correcting codes, which means that if this epsilon is encoding operation from logical to physical systems, so green is logical, gray is physical. Okay. The covariance means that if you first rotate your logical qubit and then encode, it can be represented as first encoding and then rotating on a physical level. Okay, with some covariance property where these unitaries depend on the parameter, and this dependency is represented by some group action. I see I'm short of time. Okay, so I will just here I focus on very simple case where our unitaries are just single parameter unitaries, like in this single parameter metrology. Okay, so they are generated by this single generator. Okay, so I just want to sell you this idea. So if you now consider some error correcting encoding operation, then you have some noise, then you have recovery operation, and you hope to recover ideally this logical operation, and then you repeat this process, then you obtain in the end some quantum state. Okay, and now because of covariance property, you can move this logical operations into the physical layer, and if you do so, you now can realize that effectively what's going on here can be regarded as a special case of a quantum metrological adaptive protocol where you want to estimate this theta, okay, which is the parameter in this logical unitary gate. And because of that, you can use quantum metrological bounds that will tell you that this final state cannot be too good, okay? It has to be at least noisy enough not to violate quantum metrological bounds, and this implies that these quantum error correcting procedures cannot be too good. They cannot provide too pure or too noiseless final state. Okay, and so this is just an intuition. The details are in this paper, as well as an independent paper again by the Liang-Jiang group, where they follow the same ideas but obtain somehow stronger bound in the end. Okay, anyway, I just give you this message that you can now write an inequality where on the left-hand side you have epsilon, which characterizes quality of an error correcting codes. So for those of you who are in this business, this epsilon is the distance between the error corrected channel and the identity channel measured using the worst case entanglement fidelity quantity. Okay, so this is some measure of imperfection of your error correcting codes, and this statements, this inequality tells you that you cannot make a better error correcting codes than this right hand side, where in the denominator you have quantum Fisher information bound for a corresponding metrological problem that involves this unitary gates and noise, okay, for which you can calculate this bound using these formulas I showed you before with this minimization over Kraus operators and so on. Okay, I will skip this example with losses. You can obtain some more explicit formula, and I will end up with these take-home messages. So if you consider adaptive schemes with noisy channels where you want to estimate the parameter, you have three messages. If your Hamiltonian is inside this span of Kraus operators, of this noise operators, then Heisenberg scaling is impossible, but you can have a constant factor improvement thanks to use of entanglement, and it's enough to use weakly entangled states, for example, squeeze states of light or spin squeeze states. And also, if you have some more complex models that involve local correlations and so on, you can also study these problems effectively using tensor network methods. Now, the second message is that because these bounds are really strong, you can use them to get limitations on the performance of covariant quantum error correcting codes. Okay? And the last message is that if luckily in your setup, the Hamiltonian does not belong to this subspace, which we don't expect to be very common, but it can happen, or at least approximately it may happen, then Heisenberg scaling is possible, and you can design protocols that use the ideas of quantum error correcting codes to obtain this Heisenberg scale. And that's it. So thank you for your attention.
Thank you very much, Rafał. I'm sure we're going to go a round of virtual clapping. Thank you for the nice talk. So there are a few questions, especially from Mark, I see. So I'm going to stop the recording because we are at the 1 hour limit, but we can stay in the channel and discuss and take more questions. Okay.